Hi everyone, this is Mr. Lee. In this video, we are going to go over electric flux. Okay, so let's begin. So the best way to start off with this definition of flux. Now, flux is actually a term that we use in the everyday language, but simply put, it is the amount of something that goes into or out of an area. And the key idea here is actually the word area. Okay, so the different ways that we see the word flux is such as like influx. So if there's an influx of people, so let's say there is an influx of students into Reservoir High School at 7:40 a.m. Okay, so the word influx there is that the amount of students that come into the school, right? It goes up. So the area there will be the school, and the thing will be the students. Okay. There's also acid reflux. So acid reflux is like when the acid in your stomach, right? It comes like up and out of your throat. So the reflux is that the acid is coming again once out of the area, and the area will be your throat. Okay. So those are just two different examples of flux. But for us, the important thing here is just the base definition of flux. It's just the amount of something that goes into or out of an area. And right there actually starts off with the formula. So the formula for or the variable for flux is the Greek letter phi, okay, phi. And because there's different kinds of flux for physics, we usually denote that with a subscript. So we have here, all right. So this is phi with the subscript of E. And so if we're talking about electric flux, it's the amount of electric field, okay, which is a vector that goes through a area. Okay, an area actually is a vector, and that's actually not the finalized formula. We'll come back to that in a little bit. But before we do that, let's go over this idea of area as a vector. So area is a vector. So as a quick reminder, a vector is vector has magnitude and direction. So it's kind of weird to think that area has a direction. But for what we need to discuss, we have to understand that the idea of flux is something that goes into or out of a opening. So if we were to do a quick little sketch, right, of an example. So let's say this is a table, right? This is a tabletop. And if I were to ask you, all right, find me the area of the tabletop, right? And you would say, okay, the area of a rectangle is just like your base times your height. And so this right here will give you the magnitude. And for the direction, the rule of thumb is that the direction is perpendicular to the surface. So if right here, if this is your surface, okay, if we were to draw, so this is like a 3D image. If we were to draw a 2D image, my table would look something like this. Okay, so this is my surface right there, and area is always perpendicular to like that opening. And so if I were to draw the area vector, I would draw it like this. So this would be A. Okay. Now I just made A go up. You can have A go down, but the important thing is that it is perpendicular to the opening. All right. So the thing to imagine of why it's perpendicular is, let's say this table is like I don't know. It's mostly like empty space. Okay, it just has like metal bars around the outside. If things were to go in and out of this opening of a table, it would go through in this direction. Okay, it will go through up or down into the table. And so the way that we would denote that for here is that we would look at area like so. Okay, so this is like a 3D image. Now, for our examples, I'm just gonna always have the area as, it's just a good habit that I got into, is instead of a vector of just a single line like this, I like to denote the area with a double line. Okay, and the reason being is if you take a look at our flux formula, flux has the E field, which is a vector, and area, which is also a vector. So to be able to see the two different kinds of vectors, I like to denote one with a double line, and usually that's my area one, and my E field has a single line. But if you have a different color pen, you can show the different vectors with using two different colors of pencil or ink. All right, so that is area of a vector. In real life, right, we can think about flux and area as the same. For example, let's do a face, right? So face, I don't know. Let's say here we have our nostrils. Okay, so here are the nostrils, and we know it's a face because I have eyes, nose, and there's your mouth. So the area, okay, remember it doesn't have to be like a solid object. It's just an opening of some sorts, and the opening of your nostrils is like a circular area, and so I could draw like my area like this. Okay, and so when we're talking about flux, let's say we're not talking about electric flux, but let's say the flux of oxygen or the flux of air, we would say, let's just say here, we'll do air in blue, right? So whenever you inhale, right, so we have oxygen going into the nostrils, and when you exhale, I'll do this in a different color, we have I guess CO2 coming out of the nostrils. Okay, and so the idea of these vectors, okay, because vectors have direction, the direction matters a lot. We're going to go into the mathematical definition of this, and we're going to go back to the original formula. But whenever you have two vectors that are pointing in opposite directions, okay, we have to think one is positive, one is negative. If you have two vectors that are going the same direction, we can consider that to be both positive. Now, to really describe this, there is a mathematical symbol for this of when the vectors line up. So if you remember from mechanics, okay, when we talked about torque is F cross R, right? And this is what we call a cross product. So as a quick reminder, if you, let's say we have a bar and that bar is hinged here, right? So this is the axis of rotation. And let's say you were to apply a force. All right, so this force versus this radius vector r, we can see that it makes a 90-degree angle. And the more unaligned something is, that's great for cross product. Okay, so the idea for here, if I were to jot down my notes there, I would say cross product looks at how unaligned two vectors are. Okay, so here my radius vector r and my force vector F, they are very much aligned, which means that you have maximum torque. And the way that we describe this in terms of formula, we said it's Fr, of course, absolute values, sine of theta. Okay, and the reason why we use sine theta is here, sine of 90 degrees just gives us 1, right, 100%. So what this means is that your F and your R are 100% unaligned. Okay, which results in maximum torque. So for flux, if you go back to my breathing example, we don't care about how unaligned the vectors are. We actually care about how aligned it is. And so if I were to write that down here, dot product cares about how aligned your vectors are. So for example here, right, if we have a vector A and we have a vector B, okay, and right there that's 90 degrees. If we're looking at dot products, so A dot B, this would give us 0. And the reason why it's 0 is because dot product, unlike cross product, the alignment matters. So we can see that A and B are not aligned at all. So if we know that cross product uses sine theta to describe how unaligned something are, dot product, we use the cosine of theta. So if we were to put this into a formula, right, we would say A dot product B equals 0. All right, so that means that A, B, cosine of 90 would equal 0. And we do know that cosine of 90 does in fact gives us 0. Therefore, A dot product B gives us a overall 0. All right, but what if we have A here and we have B here? Okay, so we're looking at how aligned A and B are. And so here, A, B, the angle in between these two vectors, your theta, is actually 0 degrees. And so if we have AB cosine of 0 degrees, we will get a maximum or 100% of A times B. All right, but what if, okay, so if we go back to my example here, so when they are perfectly aligned, we're looking at this area here and the CO2 coming out, right, perfectly aligned. But what if they are aligned but pointing the opposite direction? So here we have A, and then here we have B, and so this angle right here is 180. So if we have A dot product B is AB cosine of 180, it shows us that we are 100% aligned but pointing in the opposite direction, and cosine of 180 gives us -1, and that -1 just denotes that one of the vectors is just pointing in the opposite direction of the other, but this 1 tells us that we are 100% aligned. So A dot product B would just give us -AB, whatever that would give us. All right, and just one more example for prosperity's sake. Let's say we have A like this and B that looks like this. Okay, so if we were to break this down into components, this A vector we could describe as this is AY, and right here this is AX. And so if we were to take a look at AY versus AX and compare that to B, if I were to ask you, hey, which one of those components is aligned with B, you will say, well, Mr. Lee, of course that's AX, right? And so if we take a look at the way that the angles are, right? So if that angle right there, if we call this theta, AX would actually be a cosine of theta. Oh, you see where that cosine comes into play, and so AX is equal to a cosine theta, and AX, therefore AX times B will give us AB cosine theta, right? Which is just a proof of the dot product in itself. Okay, and so essentially you're just multiplying AX times B because only AX is aligned with B and AY is not aligned with B. Okay, so that's just a very brief synopsis of dot product. Let's go back. Right, let's go back to this formula here. And so if we take a look at this formula here, the question now becomes, are we looking at dot product or cross product? So the definition here is just the amount of something that goes into or out of an area. And so if we care about how much goes into or out of an area, okay, that is in fact a dot product, because you know, in order to go through this table, right, we have to move in a perpendicular direction, or in a in the opposite direction here. All right, so it's a dot product there. And so another way that you might be able to see this is the absolute value of EA cosine of the angle. All right, so that's electric flux, the definition, and let's go through let's go through the units. So for electric flux, the units are, well, let's see. The units for E field is newtons per coulomb, and we get this if we look at F is equal to EQ. The units for force is newtons. The units for charge is coulombs. So this gives us the units for the E field, and the units for area is meters squared. So Newton meters squared per coulomb are the units. Okay, wonderful. Now let's go over a couple of examples and scenarios that you might see. So whenever you are doing an example problem, I cannot emphasize this enough, but the sketch itself is the most important part. So let's say we have a cube. Okay, so on your notes, make sure you draw a nice big cube, because we're going to be sketching all over it. Okay, so we have a nice cube. And what I'm going to do next is I'm actually going to draw the area vectors. And I'm going to do this in a different color ink, but if I were to just do this with like a pencil, I would do a double line to represent the area vectors. So the area vector coming out of this area, right, look like this, look like this. This is like a 3D image, but we got that. We have the area vector here. Okay, and then we also have the area vectors going through here. All right, so these are all my area vectors. We're going to call this, we'll call this 1, 2, 3, 4, 5, and on the opposite side over there, we have this area vector A of 6. Okay, so we have this cube, right? This is a 3D space that we're trying to observe. Okay, now it could actually represent a physical object, or it doesn't have to, but that doesn't matter for flux. Okay, if it's physical or if it's just like this conceptual, this like little cube in space, and what we're trying to see is, okay, what if we have a E field? So my E field, these are my E field vectors, okay, and they are running along this horizontal axis. So as this E field is going through this cube, right, I'm going to draw my E field here as well. So now you could see how drawing the area vectors differently than the E field vectors is going to come into play. All right, so here we have E there, making sure I draw a E field wherever there is an area vector. Okay, so if I were to ask you, what is the total or the sum of the flux for my cube? Okay, so let's do this in order. Let's start off with A1. So if I look at A1, I see that, well, let's start off with my formula, right? So E dot A. I see that my E field vector and my area vector are perfectly lined up, right, along the x-axis, but one's pointing to the right, one's pointing to the left, and therefore we have negative EA. All right. Now let's go to A2. So if I look at A2, I notice that my area vector and my E field vector, they are perpendicular to each other. Therefore, my flux for 2 would be 0, okay, because they're very on the line. And by symmetry, I can see that here, E5 would also be 0 because these are perpendicular. And it's kind of difficult to imagine this, but in this like 3D space here, this right here is let's see if I could just draw this area vector here, right? So if that's my area, right, this is a 90-degree angle, and because that's a 90-degree angle, we can say this flux E of 4 is 0, and subsequently over here, E flux of 6 would also be 0. So we have negative EA here, 0, 0, 0, and 0. And if we take a look at the flux for location 3, we see that they are perfectly aligned up, and so we have EA, but this is positive. Okay, so if I were to look at the sum of all the electric fluxes, okay, I would have to add up flux 1, 2, 3, 4, 5, and 6, and what we end up with is, let's see, so for 1 we have negative EA plus 0 plus 0, and plus 0, 1, 2, 3, 4, 5, and let's see, EA. I don't think I went in order there, but we can see here that the sum flux of all this is actually equal to 0. Whoa! And the reason why we went through that example is because this is one of the hard and fast rules of physics. Okay, so let's jot that down. So the rule is, let's see, if you have any enclosed surface, okay, so our cube was the enclosed surface, and the E field is external, okay, that means that the E field came from an outside place, right? So it could be like from a, let's say like a positive rod here, right? So if we have this positive rod will create this E field there. Okay, so that's why I say external E field. The electric flux will always be 0. All right, it'll always be 0. Cool. So subsequently, right? What about the opposite? What if the E field is interior? What if the E flux is interior? So let's go through the same idea. We're not going to go through all of the drawings, but let's say we have that cube, and let's say we have a positive, charge there. Okay, and so you can imagine my areas looking like this, right? So we're going to answer this conceptually. Okay, so we have my areas that look like this. So in a conceptual manner, if I were to look at the E fields that's emanating from this, right? So this is my E field emanating from this positive charge, right? And if we were to draw this E field going through the surface, oh look, we have the E fields actually going out of the surface that is parallel to the areas. Okay, so in that case, if the E field is internal, If it's internal, it's enclosed, your E field will not be 0. So let's write that down. If you have any enclosed surface and the E field is internal, the E flux will never be 0. Okay, that is if and only if you have a actual E field. Right, so for example, if we had a positive and a negative, that rule does not apply. Okay, but here, if we just have a overall net E field, the E flux will never be 0. Cool. All right, and the very last thing I want us to go over is the calculus definition of this. All right, so let's take a look at a quick sketch. So let's say we have a piece of paper, right? So this is my 3D image of the paper, and my area is going through like this. And let's say my E field is running parallel. So I'm going to write that rule over there. So my E field is parallel to my A. We have therefore our E flux is 100%, okay, of whatever that is. So it'll just be EA. All right. Now, what if we take that piece of paper? Oh, by the way, the sideways image would look like this, right? So this is our A, and our E field would look like this. Okay. So what if we get that piece of paper and we like bend it, but the E field source stays the same? So if we bend that piece of paper, okay, the E field source is still going to be the same. I'm going to do my E field as a dotted line, okay, so it's a little bit lighter because I'm going to be drawing a lot of area vectors here. Okay, so the area vector, the only one that stays the same is exactly in the middle. I'm just saying, like, due to symmetry, that's the only one we didn't adjust. Okay, but the paper up here, because it has to be perpendicular, right? So it's a little bit hard for me to draw right there, but that will be the A, and this will be the A, and this will be the A, right? Because the rule is the area vector has to be perpendicular to the opening, or has to show what the opening looks like. Right, so these are all my my area vectors. So we can see that we like before all my area vectors faced the same direction, but when we bent the piece of paper, right, we are actually adjusting the area vectors as well. So what we're seeing is up here, because the area vector and the E field are very much not aligned. So here we can say our flux is very small, okay, because it's not aligned at all. But over here we can see, here we have a max. We have a maximum flux. We have max flux. But if the question is, what is the total flux of the system? What you have to do is you have to find each and every flux of every little tiny bit of piece of paper. And I'm phrasing that very carefully because that should sound a lot like calculus, right? So when you take a tiny bits of every tiny little thing that you can, and then you sum it all up, in terms of calculus, what we're doing is we're actually taking the integral, okay? And so the integral form of E flux will look something like this. So the total of, usually it's a uniform electric charge, but that doesn't have to always be be true. But for example, it was a uniform electric field, but our area itself was changing, okay? Because the direction of the area itself was what was, you know, that's what was being adjusted. And so this here would be the calculus version of the of a non-uniform area. All right, see you next time. Bye-bye.